Hi, everyone. Welcome to this new seminar of the series QuTech360. Today with us, we have Mohamed Abobeih, and he will give a talk about fault-tolerant operation of a logical qubit in a diamond quantum processor. Now, before we dive into it, I will present our speaker. So Mohamed is a postdoc researcher here at QuTech in the Taminiau Lab. For his master degree, he studied photonics and graduated in 2015 from 3 different institutions. So the Karlsruhe Institute of Technology, Aix-Marseille University, and the Institute of Photonic Sciences in Barcelona. After the master, Mohamed joined QuTech in Taminiau Lab, where he worked with spins in diamonds for application in quantum sensing and quantum information. Last year, Mohamed received the Kavli-Delft Publication Prize for a paper on the atomic scale imaging of a large nuclear spin cluster. So, very exciting. Mohamed, I will leave the floor to you. And please, everyone, if you have questions, you can just unmute yourself and go ahead. And at the end, we will have a Q&A session anyway with Barbara Terral, who will moderate it. Great. Thank you, and have a good talk.
Thank you, Gracia. Thank you for the introduction. Good afternoon, everyone. Today I am, as Gracia said, I'm going to talk about our recent work on fault-tolerant operation of a logical qubit in a diamond quantum processor. And this work was done in collaboration with Yang Wang from the group of Barbara Terral. But before I come to this topic, I would like to start with a rather broad introduction to MV centers in diamond and our motivation for using these systems for quantum information processing. So the MV centers in diamond, also among other color centers in diamond and other materials, such as, for example, silicon carbide, are versatile systems for quantum technologies, such as quantum sensing or quantum networks, communication, and computation. So, as you may know, one of the main goals and applications that we will focus on here at QuTech is the so-called quantum networks. So the vision here is that we would want to have multiple nodes of MV center in diamond. For now, this could also be, as I said, other defect centers or rare earth ions, or any also other quantum systems. These nodes will be connected or entangled via photonic links, and each MV center in this node is also surrounded by a nuclear spin environment. In this case, carbon-13 spins. So this carbon-13 spins serve well as qubits to store and process quantum information. So, well, our motivation for building such networks is that these networks would be quite useful for network-based quantum computation and long-distance quantum cryptography and communication. So also these networks have quite some advantages. So the system or these networks can be scaled up due to modularity, because this network can be built up of modules, and then you can scale up the system by making up many of these modules and connecting them. You can also have flexible connections between the network nodes. And for quantum error correction purposes, this could also be advantage that we can expect the errors between these nodes to be uncorrelated, which is also quite important for quantum information processing. Right. So on the photonic link side, or the remote entanglement, there have been a lot of fantastic experiments going on, and in particular from the group of Ronald Hanson here at QuTech. So, for example, this famous loophole-free build test, where the entangled two MV centers that are basically 1.3 kilometers apart. More recently, they also showed more sophisticated protocols over a quantum network, such as entanglement distillation, and most recently also a multi-node network that basically have here three MV centers or three node network, which is really the state of the art in the whole quantum network field. All right. So in this talk, I'm not going to cover this photonic entanglement lengths, but I will focus on one of these nodes, basically how to control the qubits in such a node. So I will first give a short introduction to the MV center, and then I will introduce you our quantum processor, which is basically this carbon-13 nuclear spins around the MV center. How do we detect and control these nuclear spins? And finally, I will come up to our recent results on fault-tolerant logical qubits. I should note here that by fault-tolerant logical qubit, we mean that it is a logical qubit of a fault-tolerant error correction protocol. So we don't mean here that we are working below threshold and we can do arbitrarily long quantum communication, quantum computations here. All right. So the MV center is a defect in the diamond lattice, where a nitrogen atom replaces a carbon atom, and that happens to be next to a vacant site in the lattice. So there is an electron spin associated with this defect, and this is a spin one system that can be optically initialized and read out, and it can be manipulated by microwave pulses, fast and efficient. So just to give you an idea, this is how our sample typically look like. So this little square here is our diamond chip. If we zoom in, this is what we find here. So on top of an MV center, we fabricate solid immersion lens to enhance the photon collection efficiency. We use microwave lines to send on a chip microwave lines to send microwave pulses to manipulate the electron spin. So this is a fluorescence image of the MV center right in the middle of this. So this is what we typically like a typical MV center that we use for our work. Right. So we also work at a temperature of 4 Kelvin, such that the electron spin relaxation is negligible at this temperature. So a few years ago, we did this experiment where we would prepare the electron spin and eigenstate, and then measure how long does it stay there at this temperature of 4 Kelvin. So we found out that by suppressing background microwave and laser noise, that the electron spin relaxation time is more than 1 hour. So basically, for our purposes, it is infinite relaxation time. We don't worry about the electron relaxation anymore. All right, so that was just a very short introduction to the MV. So now what about the coherence of the electron spin? So the diamond lattice is mainly made of carbon-12 atoms, which are spinless systems. But nearly about 1% of the carbon atoms around this MV are carbon-13 isotopes, which are spin half. So these carbon-13 spins are coupled to the MV center and to each other. So they flip-flop with each other all the time, and thus creates a random magnetic field around this MV center. So this path of carbon-13 nuclear spin can be seen as a source of noise from the electron spin perspective, and it's basically what limits the electron spin coherence. So T2 star, which is the coherence time measured in a Ramsey type experiment, is roughly 5 microseconds for the MV center. But we can greatly enhance this coherence times by using dynamical decoupling sequence. So we can decouple the electron from this nuclear spin path by applying pi pulses back and forth, as shown here. And we did this experiment a few years ago where we have shown that we can enhance the electron spin coherence time nearly by 6 orders of magnitude, from going from 5 microseconds to 1.5 seconds. So this dynamical decoupling of the electron spin works really well, and we can greatly enhance the electron spin coherence. Okay, so now I would like to move into the second part of my talk, which is basically how do we control our quantum processor? How do we detect and control these nuclear spin qubits? So as I just mentioned, these nuclear spins can be seen as a noise source, but we can also turn them into a resource. Well, basically qubits, if we can precisely control them. And then the question is, how would we detect and control these nuclear spins? So for that, we use the electron spin as a quantum sensor to probe this spin environment. So the idea is quite simple. You can imagine each nuclear spin in the environment as a tiny source of magnetic field. So from the electron spin perspective, the phase accumulated due to the signal is basically 0. But if we would flip the electron spin back and forth in resonance with the signal, we kind of rectify the signal, and we would see this as a coherence collapse in our signal. So now different nuclear spins in the environment couple differently to the electron spin, and that leads to their precision frequencies to be different or shifted from each other. So each nuclear spin would normally persist at a different frequency. And this allows us to basically detect these different nuclear spins because they have different evolution frequencies. So if we would prepare, for example, the electron in a superposition state, let's say X state, and then apply this sequence of dynamical decoupling pulses and sweep the time between these pulses, which we call here tau, and then measure the remaining coherence in the signal, we will get a dip in the coherence signal if this time is in resonance with one of these nuclear spins. So as you vary the time, it might hit a resonance of one of these nuclear spins, and then you would see a dip in the signal, and you know that this is a nuclear spin around this time. So this is actually what we do here in this experiment. So we prepare the electron as superposition, apply this pulse, a sequence of pi pulses, and then vary the time between them. And this is what we get. Quite complicated spectrum, but it's all well understood by now. So if I would zoom in, for example, on this first part of the signal, we would see this a lot of coherence collapses or sharp dips in this signal. And it turns out that these dips correspond to single nuclear spins in the bath. So at each of these dips, just the electron, the time between the pulses hits the resonance of one of these nuclear spins, and we see a coherence collapse in this signal. So in this case, the signal was, if we just do a manual fit, we will find out that it is explained by 7 single nuclear spins. And so also more recently, we used machine learning methods to do fitting of these complex signals, and we found that more than 30 spins we found that we can detect more than 30 spins in this complex spin. So one more thing here, you might notice this broad coherence collapses in the signal, and these are basically due to strongly coupled nuclear spins in the bath. So if you have 2 carbon-13 nuclear spins that happen to be close to each other, this would create this broad coherence collapse in the signal. So this carbon-13 pairs can also be used as qubits or memories with exceptionally long coherence times. But in the rest of this talk, I'm not going to talk about these pairs of carbon-13 nuclear spins. I'm mostly going to talk about this individual nuclear spins that we use for our work on quantum recursion. All right. So this is about the detection of nuclear spins. Then how about the control? How would you control these nuclear spins? Now, it turns out that these two things are quite similar in it. So, and to have a better understanding, let's first have a look on the system Hamiltonian. So if we put the electron spin in ms equals 0, this would be the Hamiltonian of the, let's say one of these nuclear spins around the MV. So this nuclear spin would evolve with a frequency given by the external magnetic field, and it will rotate along an axis given by the external magnetic field direction. So if we put the electron spin in ms-1, then we turn on the hyperfine interaction between this spin and the nuclear spin, and we get this extra term in the Hamiltonian here. So this will lead this nuclear spin to rotate along a slightly tilted axis with also a different frequency. So these axes are non-commuting, so they are not parallel to each other. And if we flip back the electron spin between this 0 and -1, we can have a complete selective control over these individual nuclear spins. So basically, if we would apply a dynamical decoupling sequence and choose the time between these pulses to be in resonance with one of these nuclear spins, we perform a controlled rotation gate, like the one shown here. So by choosing the right interpulse delay and number of pulses, we can do a maximally entangling gate between the electron and nuclear spins. And this is what allows us to universally control these nuclear spins. All right. So actually, in the dynamical decoupling signal that I just showed you, the more accurate picture there is that the electron spin is getting entangled with this nuclear spin when the interpulse delay or tau is in resonance with the nuclear spin dynamic. And that's why we get this coherence collapse in the signal. This is just the more accurate description of what we have seen earlier. All right, so far I have shown you how to roughly characterize the nuclear spin environment. That is basically to measure the coupling between the electron spin and some nearby nuclears. So, but how can we more precisely characterize this spin environment? For example, to know where is each spin with respect to the MV center, or in other words, to obtain a 3D image of the system. So it turns out that this problem is interesting from both quantum information and quantum sensing points of view. For the quantum information side, obtaining such a 3D image would provide a precise description of the system Hamiltonian, which is necessary for better understanding and optimal control of the system. For the quantum sensing side, this cluster of carbon-13 nuclear spins provide a model system to study and develop methods for atomic scale magnetic resonance imaging, which is a very active research area in quantum sensing, especially with MV sensors and banks. So, okay, how would we obtain such a 3D image? The basic idea is that these nuclear spins are also coupled to each other by dipolar coupling. And this coupling can be weak, but if we can measure, how each of these nuclear spins couple to each other, we basically would reveal the composition and interconnectivity of this cluster. And then we can transform this measure coupling into a 3D structure or image of the system. And in this paper, this is what we actually did. We developed multi-dimensional spectroscopy methods to very precisely measure the coupling between all of these nuclear spins, even if they are very weak, below even 1 Hertz. We could measure them. So we did this experiment. So for the device that we are using throughout this work, this is the coupling spectrum or table that we got. So we basically here detected 27 carbon-13 nuclear spins and measure the coupling between them. So this measurement took roughly 350 hours. So after that, we took this coupling matrix or spectrum and then transformed it into a 3D image of the system, and this is what we got. We were able to locate each of these 27 nuclear spins with atomic scale resolution. So basically, the uncertainty in the position is below 1 angstrom, or the diamond bond length. We also built an actual 3D model of the system. I guess many of you in QuTech might have seen this already. So what we see here is a model of our MV center. So these white balls are the carbon 12 atoms, which don't have a spin. And then this is the MV center. And the yellow ones are these carbon 13 spins that we use as qubits to store and process quantum information. All right. So just to show you some examples of how we use this device. So in this work, we took just 8 carbon 13 nuclear spins in addition to the nitrogen nuclear spin and the electron spin of the MV center, and demonstrated a 10 qubit quantum register with quantum memory up to 1 minute. So basically what we did is we demonstrated pairwise entangled states between all the spins in the register. We also showed that the nuclear spins in this register can be used as excellent quantum memories with coherence times more than 10 seconds for the carbon 13 spins, and more than a minute for the nitrogen nuclears. Also used basically different nuclear spins in the device as a quantum simulator, and we use that to demonstrate a many-body localized discrete time crystal. You can find more about this in this recent paper. So, okay, with this, I come to an end of my introduction to the MV center and our quantum processor, or how do we detect and control the nuclear spin qubits. So now I would move into our more recent work on this fault-tolerant logical qubit. I don't know how would we do this. Should I stop here for taking some questions, or leave them till the end, or?
Let's see if there are any questions. We could also take them now. Are there some questions?
Yes, I would have a question, if I may.
Please.
So yeah, for the 3D mapping, I didn't quite get how you find the precise 3D coordinates. I mean, I understood how you get the distance from the carbon to the NV center, but how did you get the 3D coordinates?
So okay. So here, what we do is we measure how each of these nuclear spins couple to each other, right? So basically, this gives you the structure of the nuclear spins. Let's say you can take this spin as your origin, so it gets you the structure with respect to that spin. But what we also did, of course I didn't explain that part. In this work, we also have the nitrogen vacancy here. It has a nitrogen spin, and this what we did, we also measured the coupling between these nuclear spins with respect to this nitrogen spin. So we're also able to locate this cluster with respect to this nitrogen spin. So we know how are they all located with respect to the nitrogen vacancy center. Does this answer your question?
Yes, more or less. I still don't quite get how you are now able to distinguish whether the carbon nucleon spin is in this picture above or beneath the nitrogen.
Yes, that's a good question. Because in this case, the coupling depends on also the external applied magnetic field, right? So this basically also breaks this symmetry. So if you in you would have in a diamond lattice, you would have 4 equivalent positions. But if you would apply the magnetic field, so the 2 nearest neighbor atoms would have, the ones that are along the field would have stronger coupling compared to the other ones. So basically there's also an extra information coming from the external applied magnetic field, which is along this MV axis. So this is basically what also allows us to distinguish if they are above or below, because the coupling would be different. Yeah.
Okay, great. Thank you.
Yeah.
I see from the chat that also, Lieven, you have a question?
Yeah, thanks.
Go ahead.
Yeah. So Mohamed, when you were to take a new NV center and if you begin to characterize the coupling between all the carbon spins in the nitrogen Vixie center and also the carbon spins amongst themselves, how long does it take? Is this a matter of days or weeks or months? How long are you busy characterizing?
Yes, this is a good point. But I think, over of course, for the first experiment that we did, this was taking time because we were also learning how to do this. But over the years, we have developed more automatic ways to do this characterization. For example, I mentioned this machine learning paper that we developed in collaboration with a group in South Korea, that we can basically automatically characterize the coupling between the MV and this carbon-13 spin. That works quite well and quick. So I mean, just what I would need to do, a few hours record spectrum, and then also use this machine learning technique to basically know roughly how each of these nuclear spins couple to the MV. That can take, I would say, maybe a day or so, or that order. Then the imaging part, that still takes time, but we are also working, on methods how to automate this process and how to make it faster. Because the way we did it in that paper was still kind of manual. We record the spectrum manually and analyze it also one spin by one. But of course, the goal there is to also develop more automatic routines for making this process faster.
Okay.
Yeah.
Thanks. Yeah. And a brief follow-up question. So is there often a need for you to go on to a new NV center, or do you actually keep using the same one because it's just fine for the next experiment? How often do you switch samples, basically?
Yeah, for my entire PhD, I used one NV actually. So it's not necessary to switch between NVs. I mean, it's randomly chosen one, and I think it's also fine. So you don't need to switch samples. But of course, if you would like to go over network or so on, you would need more of these samples. So you would need. So it's always an important question how to characterize the samples quickly, and also because we would need to use more of these samples in a network for sure. Yeah.
Okay. Thanks.
Okay. If there are no more questions, we can go ahead.
Right. Okay. So now come to the last part of my talk, which is a fault-tolerant operation of a logical qubit. So as most of you may know, large-scale quantum computers will require overcoming imperfections. So the basic idea, or the main idea there, is to use so-called logical qubits, which are encoded in multiple entangled physical qubits, so that errors can be corrected. And second, all building blocks must be fault-tolerant, so that reliable operations are also possible despite having noisy elements. Should mention here that by fault tolerance, we mean on the lowest level, any single error should not lead to a logical error. There have been a lot of beautiful experiments towards fault tolerance. For example, experiments on error detection code, where errors can be detected but not corrected. So we have this two nice examples. This work from Leo De Carlos group, and this work from Christian Andersen when he was in ATH. He's also now a group leader at QuTech. And also error detection code were also done in iron. Also, we have non-fault-tolerant error correction protocols, where some but not all types of single errors can be corrected have been demonstrated using a variety of physical platforms. For example, superconducting qubits, trapped ions, and solid-state spins, including this work from our group by Julia Kramer. All right. So more recently, fault-tolerant error correction protocols have been achieved using ion traps. For example, this nice experiment from Chris Monroe group, although done with destructive stabilizer measurement. And more recently, this wonderful work from Honeywell, where they do multiple rounds of fault-tolerant quantum error correction. So the now question is, can we also get into this regime with solid-state spins, where we can do fault-tolerant operations on the logical qubit level? So the question is, okay, what is the smallest fault-tolerant quantum error correction code that we can implement? So many of you probably know the famous 5-qubit code, which is sometimes called the perfect code. This is the smallest universal error correction code that can correct any type of single qubit error. So, however, the exacting error syndrome using a single ancilla qubit, like what's shown here, is non-fault tolerant, because a single qubit error on the ancilla can propagate into ways to error, which leads to a logical error. A couple of years ago, Chow and Reichert came up with a very nice scheme that uses only an extra flag qubit to make this scheme fault tolerant. So the basic idea is that the errors that would propagate into ways to errors, single errors like this one that would propagate into ways to errors, would also propagate to the flag and will trigger it. So in their paper, they show that these errors are also distinguishable by their syndrome, and therefore can be corrected. So in this work, we would like basically to implement this smallest fault-tolerant logical qubit. So we use our 27 quantum processor, which was recently characterized, as I mentioned earlier. We use 5 carbon-13 nuclear spins as our data qubits. We use the MV electron spin as our ancilla, and the nitrogen-14 nuclear spin as the flag qubit. We then demonstrate fault-tolerant encoding, gate operations, and stabilizer measurements. We did not show yet a full cycle of quantum error correction, which would require repeating this stabilizer many more times. But our stabilizer measurement is non-destructive, so the post-measurement state is available for further processing, and we use real-time feed-forward based on the measurement outcome. So we thus show all the primitives for fault-tolerant quantum error correction. All right. A key ingredient for quantum error correction is the ability to perform non-destructive stabilizer measurements and to apply real-time feedback based on the measurement outcome. So here we first test this capability on a simple scenario. So by using such stabilizer measurement to deterministically prepare an entangled state. So we initialize the qubits in all 0 state and then measure this stabilizer. And based on the measurement outcome, we would either prepare the GHZ state with a plus or minus sign. So now if we would take this measurement outcome into account and do real-time feedback to apply this Z operation here, we can deterministically prepare this GHZ state with a plus sign. So after that, we do a tomography of the state by measuring all non-zero terms that define the state, and we find a state fidelity of 86%. This is quite relatively high for a 4-qubit GHZ state. So we can say that our stabilizer measurements work quite well. All right. Now I will move into how to do logical state preparation. So the first question is, can we prepare the logical state in a fault-tolerant way? So fault-tolerant encoding or preparation means that any single fault in the encoding scheme will not lead to a non-trivial weight 2 error in the prepared state. So basically, any single fault will not lead to a logical error. So in their paper, the one that I just showed, Chow and Reichert showed this scheme or introduced this scheme for fault-tolerant state preparation. But this scheme is not native for our gate implementation because it uses many C-phase gates between these data qubits, which in our case would be this nuclear spin spins. So that's not the most favorable scheme for our physical platform. So instead, Yang and Barbara developed a more suitable encoding scheme for our platform. The scheme relies on multiple stabilizer measurements. So let's say we would like to prepare the logical minus state. The basic idea is that we would initialize our qubits into this state, which is an eigenstate of this first two operators. All of these operators are just the minus logical X operators. So we prepare this state into an eigenstate of these first two operators. And then we measure the rest of these stabilizers, P3, P4, and P5. All right. By measuring these other three stabilizers, we would prepare the target logical state, but in a non-fault-tolerant way. So this procedure can be done by conditioning on the measurement outcome to be +1, or by accepting any outcome and doing Pauli frame update. So in this work, we choose to do it in a conditional form because it gives higher fidelity as certain ancillary outcomes are more reliable. But as I said, this first part is non-fault-tolerant preparation. Basically, some single faults in this part can propagate into way too logical errors. So by adding this verification step, which consists of these two carefully constructed stabilizer measurements and a flag ancillary check, we can herald successful fault-tolerant state preparation of the logical qubit. The heralding criteria are, first, the outcomes of these two stabilizers, T1 and T2, have to be compatible with the other stabilizers. So in this case, we have all the stabilizers, we condition on them to be +1. So the measurement outcome of T1 and T2 also has to be +1. And the second criteria is that the flag is not raised. So once we meet this criteria, we can deliver at the end of the sequence a logical state that we can still process and use for further quantum information process. So we just herald the successful fault-tolerant preparation of the state. All right. So how would we do? How would we implement this experimentally? The first thing is we need to initialize our data qubits. So the electron spin can be directly initialized by optical means, as I mentioned, just shining in some resonant laser for some time, then can initialize the electron spin directly. But the nuclear spin, the carbon-13 spins and nitrogen spin have to be initialized via the electron spin.
So as I just said, these nuclear spins need to be initialized via the electron spin. So what we do is we first initialize the electron spin into a certain state, and then do a swap operation with these nuclear spins to initialize the nuclear spins one by one. And this takes roughly 12 2-qubit gates to do initialization of all of these 6 qubits. So this is the first step: initialize the qubits. After that, we need to replace each of these 2-qubit gate by its equivalent in our native gate scheme. And then, so we replace controlled X by this by its equivalent, and controlled Y, and so on. And then finally compile the single qubit gates together to reduce the circuit complexity. By doing so, this is the circuit that we get. It's quite complicated circuit. It involves up to 42 qubit gates. Because of this large number of gates, the total sequence time is much longer than T2 star, which is around 10 milliseconds. So we have to use echoes to mitigate this decoherence. And with echoes, our T2 can be more than 10 seconds. We also need to mitigate the effects of the decoupling because these nuclear spins couple to each other. So we do that by using asynchronous echo sequences. And this echo also requires precise timing of all the operations. So now we would like to test this experimentally. So the first important question is how to characterize the prepared state. So let's say I'm going to run this circuit. Now, how can I characterize this prepared state? For that, we define what we call the logical state fidelity, which is the probability to have at most a single qubit error in the prepared state. So to measure this, we need to calculate the overlap between the prepared state and the target state up to single qubit error. This is the formula that we get. We basically need to measure these expectation values to be able to calculate this logical state fidelity. So we did that. We measured this 31 operators that define the state. And from that, we calculate the logical state fidelity. We find that the logical state fidelity is 82% for the non-fault-tolerant scheme. It's basically this part without the verification step. And it's 95% for the fault-tolerant scheme, including this fault-tolerant verification step. All right. To better understand this, we can look at the error distribution for both fault-tolerant and non-fault-tolerant preparation. For the 5-qubit code, any prepared state can be decomposed into its overlap with the logical minus state plus 0 or single qubit error, and the opposite state, which is in this case logical plus, with a 0 or single qubit error. So these are 32 states in total. These 32 possibilities can be grouped into these two parts. First, the probability to have no logical error. That's probability to have a 0 or single qubit error. And the right part is the probability to have 0 or single qubit error with respect to the opposite logical state. So these results show that the fault-tolerant scheme suppresses logical errors consistent with fault tolerance, preventing single faults to propagate into weight 2 or multiple qubit errors. So the overall logical state fidelity is improved despite the higher probability to have a single qubit error, which is due to the increased complexity of the sequence. So after fault-tolerant encoding, we then demonstrate fault-tolerant manipulations of the logical states by applying transversal logical gates. We demonstrate a complete set of single qubit Clifford gates that can basically prepare all the 6 eigenstates of the logical Pauli operators: logical 0, 1, plus, minus, plus I, and minus I. So the logical X is performed by applying 5 single qubit pi pulses along X direction. Same for logical Y. A logical Hadamard or a logical S, the phase gate, can be applied by applying this 5 Hadamard gates and doing qubit permutations. So these permutations are fault tolerant because in this case, we realize them by relabeling the qubits rather than by physically applying swap gates. Okay, an important note here is that our control system performs the underlying single qubit gates by tracking basis rotations and compiling them with subsequent gates or measurements. In the sequences considered here, such compilation does not require, does not increase the physical operation count, and therefore there is no reduction in the fidelity if we do the gates by this way. For comparison, we also implement the worst case scenario where the logical gates are applied physically. So this includes, 5 single qubit gates and the corresponding additional echo sequences before and after. So this increases circuit complexity. And in that case, we see also a little bit of a reduction in the logical state fidelity if we do it that way. All right. So after demonstrating fault-tolerant encoding and gates, we finally demonstrate and characterize a flagged stabilizer measurement on the encoded states. So such measurements are the key building blocks for fault-tolerant quantum error correction in this code, these flagged stabilizer measurements. So first, we fault-tolerantly encode or prepare the logical minus state, and then measure this stabilizer X, X, Y, I, Y. And to ensure that the measurement is compatible with fault tolerance, the 2 qubit gates are carefully ordered, and a flag qubit is added to capture ancilla errors that can propagate to logical errors, as I explained earlier. So the resulting output in this case is 2 classical outcomes, ancilla and the flag. And of course, the post measurement state. So we still have the state after this measurement. Okay, but then how can we characterize the state after the stabilizer measurement? Again, we also measure the so-called logical state fidelity, but in this case, it's given by the probability that the logical information can be correctly extracted. So probability to not have logical error. So different when taking into account the flag measurement outcome or not taking it into account. That's because the interpretation of the error syndrome, would it change if the flag is raised or not? Right. So this is we did this measurement, and this is what we get here. So first, we find after the measuring this stabilizer that the logical state fidelity is 77% for the post-measurement state, done without any post-selection. But because, and here we compare the 2 scenarios when we have the fault-tolerant scheme and non-fault-tolerant scheme. So when we don't insert any errors on the ancilla, I mean, just we use the natural errors on the ancillas, which are naturally also rare in this case, we don't see any big difference between the fault-tolerant scheme or non-fault-tolerant scheme. But if we would on purpose also insert, for example, a Y error on the ancilla here, this error would also propagate into a logical error, but it would also propagate to the flag, and the flag would catch it. So for the fault-tolerant scheme, for which we take the flag outcome into account, we will find that we can the logical state fidelity will be much higher than the non-fault-tolerant scheme, where we don't take this flag outcome into account. So basically, this non-trivial error is detectable and remains correctable. So the logical state fidelity is partly recovered. Whereas for the non-fault-tolerant case, it already goes below 0.5. So it means that on average, the state is also flipped to the other side. So it's quite a fatal error in this case. All right. So with that, I come to a conclusion of my talk. So I hope that I've shown you that MV centers are promising platforms for quantum technologies in general, communication, computation, simulations, and also sensing. I have shown you our recent results on fault-tolerant operation of a logical qubit with solid-state spins. So that includes fault-tolerant encoding, fault-tolerant gate operations, and stabilizer measurements. And the question now is, what is next, of course? So first, we would like to improve this control fidelities, or two-qubit gate fidelities. Then we also need to improve the optical entanglement links to be able to scale up the system, for example, by using optical cavities or maybe even using other defects or systems. So this would enable us to scale up the system to perform larger scale quantum computation. And finally, while the work that I've shown is for quantum error correction, it's mostly just on one local node. But the final goal is to do quantum computations over a network. And there we would perhaps need to use different error correction protocols, for example, over a network protocol. And there have been some nice proposals for this. For example, this nice paper from Nickerson in 2014, where you can also do, for example, surface code over quantum network. And this is perhaps is the future of this systems. All right, with that, I come to the end of my talk, and I would like to thank again our collaborators, Young and Barbara, and the rest of the Taminiau group, especially Joe, Connor, and Shord, who took part on this fault-tolerant work. And thank you for your attention. Yeah.
Thanks, Mohamed, for a nice talk. Sorry I was a bit late. I think Raja mentioned I would sort of chair the Q&A, but maybe let's all unmute. Who wants to mute can unmute, and give Mohamed some applause. All right, maybe I can ask a quick question before there are a lot of other questions. Mohamed, can you say something about, you talked about the logical state fidelity, but of course you have to assess this by measuring all these products of these polys, right? And they are measured also with some inaccuracy. So can you say something about how you believe that affects the logical fidelity, or you compensate for this? Or
Yes, yes, of course. Okay. Yeah, I should go here. Right. Yes. So we indeed to characterize this logical state fidelity, we measure these operators to be able to calculate this. And of course, these operators are also measured. When you measure them, you apply 2-qubit gates that introduce errors to your state. So what we did in this case, this measured operators are corrected for the readout. So basically, we characterize this readout process on simple states independently, and roughly estimate how much such a measurement would, how much errors such a measurement would introduce to your state, and we correct for those measurement errors here. So the data that I showed is readout correct. And of course, in this case, this is what we would like to do, because we would like to know to have the best estimate of the state before we apply these gates to extract the expectation values. Yeah.
Okay, thanks, Mohamed. Okay, I see a few people with raised hands. One is Lieve. I don't know if that relates to a question of earlier, Lieve.
That's a new hand. Yeah, thanks.
Okay. Yeah.
Yeah. So yeah, great talk. I wanted to ask about the comment you made at the very end, which is that to connect or entangle spins belonging to different centers, you might actually consider other impurities than the nitrogen vacancy in diamond? What would be your favorite one or ones?
Yeah, right. I mean, we already know that the EMV synthesis has also some limitations for the optical entanglement links, because basically the current rates for the entanglement generation is quite slow, and we need to push this further. So both in the group of Ronald and Tim, also considering other defect centers. For example, Ronald is now also considering Tim vacancy centers, which in that case can be integrated on for example, photonic crystal cavities. This would enhance basically this optical entanglement links much more. Also in Tim's group, we are also considering now silicon carbide. At the moment, it's hard to say, which defect would be the best for that, because it's on the one hand, like some of these defects would have nice optical properties, like for example the Tim vacancy, silicon vacancy center, silicon carbide, but also have some limitations on the spin control. So this is not fully solved the problem yet. It's just ongoing research to decide which one would be best. But it's still not, at least for me, it's not obvious which one would be the best candidate. But yeah.
Okay, thanks,
Okay,
Mohamed. Yeah, Lieve, you have. Sorry, did I hear something? Okay, I think that answers the question. There's another question from Bernard Bo. Yeah, go ahead.
Yeah, can you hear me?
Yeah.
Yeah, first of all, great talk, but I have a question about the slide right before the conclusion.
Yeah.
Yeah. So maybe it's not immediately obvious to me, but I'm wondering, what if an error happens here? How do you distinguish that? Because I don't see how you can distinguish this from this. You get what I mean?
Yeah, but okay. I mean, the point is, not all errors on ancilla would necessarily propagate into a logical error, right? Into a way to error, right?
I see.
You could have you could have an error that seems like a way to error, but it is equivalent to a single qubit error. There's a thing about 5-qubit code also, like any let's say way to error. It's not necessarily non-trivially way to. It can be either corresponding to you end up having your target logical state with a single Pauli error, or the opposite state with a single Pauli error. So yeah.
All right, I see. Thanks.
Well, maybe I can add to this. The point is, you can examine, such a circuit and insert Pauli errors XYZ at any location, and then you check how they propagate. And the idea of this flag is that gives you additional information that there should be actually a weight 2 error on the data. And so you should not infer a weight 1 error, because then effectively you make a logical error. And that's the help of the flag.
Yeah.
But you have to examine these circuits in detail to understand the full fault tolerance.
Thanks.
Actually, ask a follow-up question on that. If you say examine these circuits, do you then mean that you have to brute force try all errors and see what it gives?
That's a very good question. So, because in an ideal world, we just would do this numerically. That's to say, we'd have some software that would just take the circuit, and then we would, indeed, put these errors down and see what happens. Of course, you have to have some design principles to come up with a good circuit before you kind of brute force try all circuits, right? But for example, the circuit that Mohamed showed earlier, Yang and I had a fairly elaborate argument to show that, if the error occurs here, this happens. If the error occurs there, this happens. And that's typically done in this sort of fault-tolerant construction, also in the work that Mohamed mentioned by Chow and Reichert. But I also know from papers where they kind of brute force it, as to say they just numerically, check the insertion of errors and their consequences. Does that answer your question?
Yeah.
Okay. Okay, other questions? Okay, I don't see anything at the moment. Okay, I think it is also 5 o'clock. I hear the clock banging here. Anyhow, so let's thank Mohamed again then for a nice talk. And I'm sure that if you have more questions to Mohamed or any of the people on this project, you can just walk over and ask them, and we're happy to answer.
Okay.
All right. Is there anything about the future talks, Grazia? Anything to announce at this stage?
No, not yet, but everything will be in the QuTech newsletter, so the news will reach you.
All right, good. Okay, that's it for today then. Okay, thank you, everybody.
Thank you.